No one really understands quantum physics, not even quantum physicists. Quantum theory is the basis of modern-day physics. In a way, it's the language for all more specific theories of fundamental physics. We have to use it when we want to predict and explain the behavior of the most basic things that we know. Atoms, for example, and their ingredients, the elementary particles such as electrons. Today, I will talk about something that is rather strange about this theory. Quantum theory is not just about some weird niche phenomena. In fact, its practical importance is huge. For example, it explains why light particles can create electricity in a solar panel. You need it to explain how the parts of a computer work and ultimately the computer itself. Quantum theory is a fantastic recipe for predicting and explaining what we can measure and observe. For instance, the numbers that appear on the displays of measurement instruments in physics labs. Often, as we will see, these predictions are strikingly different from what we would have expected based on our everyday experiences. Simply said, how we expect the world to behave from what we can see with our eyes is not what actually happens on a very small scale. We know from all these observations in labs that quantum theory works, in fact, fantastically works. But in a sense, we don't know how it works and why it works. In what follows, I will tell you about the philosophy of quantum theory. I will tell you what makes quantum theory so intriguing, and I will outline 3 possible types of responses to the mysteries of quantum theory. In physics, we often describe things in terms of laws of nature. For example, that an apple falls from a tree, or that the Earth moves around the sun, can all be derived from the law of gravity. In a way, because quantum theory is the framework for the most fundamental laws of nature that we know, the laws of everyday physics somehow also depend on it. In everyday physics, billions of basic quantum objects are involved. An object, like a table, is made up of tiny quantum particles. But to see what is so weird about quantum theory, it is best to look at situations where individual particles are involved, one by one. Then we can see how different the laws of quantum theory really are from the laws of everyday life. Let's look at a famous experiment, which is called the doubleslit experiment. This experiment shows how quantum objects, particles such as electrons, behave differently from, for example, tennis balls. We have a screen, and before it is a wall with 2 openings or slits. Particles, for example electrons, are fired from one side against the wall. Some go through the slits. Those will end up on the screen behind the wall, where they will be detected. When we hear about elementary particles, we might think of something like mini tennis balls, and we might expect those particles to behave like tennis balls. Now, when you do fire tennis balls at a wall with 2 open slits, you would expect them to end up clustering on the screen again behind the slits. But for elementary particles, this is not at all what happens. When elementary particles are going through the wall with the 2 slits, and when they are detected on the screen, they form a sort of wave pattern on the screen. This is really not what we would have expected. It seems as if some balls cancel each other out and others somehow reinforce each other. In a way, as we see, the particles collectively behave like a wave. A bit like when you throw a pebble into the water and see ripples on the surface. And quantum theory predicts this wave pattern perfectly. Until now, things are remarkable, but not paradoxical or mysterious. This changes when we ask, for an individual particle, through which slit did it go? Where exactly did it travel before it was detected on the screen? Quantum theory itself, successful as it is, just doesn't answer this question. You might think, let's find out by installing little particle detectors at the slits. But now a funny thing happens. As soon as we do that, the particles all of a sudden don't behave as a wave anymore. We now know which particle was detected at which slit. But now they behave like regular tennis balls, without any waves. So this doesn't help us answer our original question. What happened with an individual particle in the original setting, when we did not look or measure? Where exactly was that particle? In a way, it seems as if nature wants to keep that a secret from us. Philosophers and some physicists, when they are in the mood for philosophy, want to know, what on earth are the particles doing while we are not measuring them? How do they behave? Broadly, there are three options to react. Three different kinds of philosophical answers to this question. The first answer is called anti-realism. According to anti-realism, things do have properties when we measure them, but not otherwise. A tennis ball is there when we look, and it has certain properties. It is round, it is yellow, it sits in my hand, and so forth. The idea here is that quantum objects only have such properties when we, in some sense, look at them. In other words, according to anti-realism, there is no objective reality where things actually exist without anyone seeing, perceiving, or measuring them. Applied to the double-slit experiment, anti-realism says that when we don't measure at the slits, the particle, an individual particle, just did not go through any of the slits at all. A sentence such as, the particle went through slit 1, or the particle went through slit 2, is meaningless according to anti-realism. Don't worry if this still sounds a bit unclear. The main problem with anti-realism is precisely that it tends to be a bit unclear. I myself developed and defended a version of anti-realism some years ago, but I now find it a bit too unclear myself. I would love to see a crystal clear articulation of anti-realism about quantum theory, but I'm simply not aware of any. The second answer is called many worlds. It says that every particle, in some sense, goes through both slits, though, to put it somewhat crudely, in different branches of reality. The idea here is that there are countless such branches of reality, not just two as shown here. Many of my colleagues really like this interpretation, because this is sort of what you get when you just read quantum theory in the literal sense at face value. But in my view, and in that of some other colleagues of mine who are also critical of many worlds, this interpretation cannot really explain how quantum theory works so well, because there is no room in this interpretation for probabilities. Finally, the third answer is that, as one would have expected, every particle goes through exactly one slit, even if we don't know which particle through which slit. This answer seems to be the most natural. The great physicist Erwin Schrödinger once proposed a thought experiment to show that this answer had to be right. The thought experiment is known as Schrödinger's cat. A cat is placed in a box with a bottle of poison. At any time, whether the poison is released depends on some random quantum process. For instance, the poison might have a probability of 50% of being released within an hour. And whether or not this happens is completely random. So whether the cat is dead or alive depends exactly on whether that quantum process happens within that hour or not. Now, when the cat is in the box with the poison for an hour, and we open the box after that hour, there is a 50% chance that we find the cat dead. But what should we say about the state of the cat before we looked? That will depend on which of the three options considered before we choose. If we choose anti-realism, we will have to say that the cat is neither alive nor dead before we look. It is simply not in a definite physical state at all until we see or measure it. If we choose many worlds, we have to say that it is both alive and dead, but in different branches of reality. Schrödinger's point was that only what I here call the third option is reasonable, that there is one single objective reality, and that the cat is either alive or dead in it at any time. We simply do not know whether it is dead or alive. At this point, it may surprise you to hear that most of my colleagues are actually not fans of this third option. And their main reason is, for this interpretation of quantum theory to work, we must assume that there are some really weird cause-effect relations, weird in terms of time and space. One option is to suppose that there is action at a distance. What we do here on Earth can have an immediate causal effect anyway, say on the moon or even in a distant galaxy, and even if there is no transfer of any stuff or material from here to there. Another option is to suppose that sometimes, crazily, causes can come after their effects. In other words, that sometimes, without being aware of it, we causally sometimes influence the past. If one wants to adopt the third answer, that there is only a single reality where we don't know if the cat is dead or alive, or through which slit which particle went, then one has to accept at least one type of such weird cause-effect relationships. My research focuses on what the most attractive option is here. What worries many physicists about these weird types of cause-effect relationships is they may clash with Einstein's famous theory of relativity, and this is our best theory of space and time. Relativity theory by itself doesn't say anything about cause and effect relationships, but the picture of time and space that it offers is just not easy to combine with the idea of action at a distance or with the idea of influencing the past. I myself am currently developing an alternative version of the third answer, but it is still a bit unclear whether that version will work. My hope is that it will turn out to be in harmony with relativity theory. So, why is quantum theory so fascinating and mysterious from a philosophical point of view? And why is it fair to say that actually no one really understands quantum physics, not even the quantum physicists? Quantum theory helps us make fantastic predictions, which have led to great technological advancements. Some of these predictions are really surprising. Think of the wave pattern on the screen behind the double slit. Apparently, physical objects at the most basic level are very different from the more familiar objects in our everyday lives. But the really puzzling question is what happens to the particles when we don't look. No one has so far presented an answer that has convinced the majority of us who are working on this problem. In that sense, no one really understands quantum physics.